Hello, my name is William Rock, and I will be giving a brief introduction to hyperspectral imaging in a course that we call Hyperspec 101. In brief terms, hyperspectral imaging is the combination of imaging and spectroscopy. Hyperspectral imaging combines the power of spatial imaging and the power of spectroscopy into a single technique that allows a scientist to leverage the chemical discrimination power of spectroscopy and the spatial discrimination of imaging, both at the same time, to give them maps of chemical content. These maps can be used in an endless amount of techniques to show where chemical content appears, both in remote sensing and on, say, a conveyor belt or in a laboratory situation. Head-Wall's imaging spectrometers operate in the region of the electromagnetic spectrum that is covered by the sun. So in this figure here, we see a cartoon of the entire electromagnetic spectrum. The solar spectrum is depicted by this green curve here, and the region of the electromagnetic spectrum covered by Head-Wall's imaging spectrometers is bracketed by these black dashed lines. And so you can see the blue end of our spectral range here and the red end of our spectral range here. And also for your reference, the visible region of the electromagnetic spectrum is shown here as well, bracketed by these purple and red lines. In order to grasp the power of combining imaging and spectroscopy, it's important to have a basic understanding of spectroscopy and how it can be used to differentiate objects or even do things as powerful as quantitation or chemical abundance determination. So all objects will absorb and reflect light in a unique way. This is easy for us to comprehend if we think about things like red or blue flowers or green grass. And the way that light interacts with these objects we see every day. So when sunlight strikes a blue flower, it will reflect more of that blue light back to our eyes, and therefore the flower will appear blue. When sunlight strikes a red flower, it will reflect more of the red light back to our eyes and absorb more of the blue and the green light, and therefore the flower will appear red. And in the same way, when sunlight strikes green grass, more of the red and blue light is absorbed and the green light is reflected back to our eyes. So in this simple way, our eyes are doing a sort of spectroscopy where they can tell what part of the sunlight is being preferentially reflected back to our eyes. So if we have greater spectral resolution, or can see the fine details of how the light is absorbed and reflected, a spectroscopist can do powerful things like determine exactly what chemical or what type of object is absorbing or reflecting that light, and then that information can be used to identify an object in a scene. And so this shows examples of the spectral responses of some common objects like pine woods, grasslands, red sand, and silty water. Of course, we all know that these objects look very different, and this is just a depiction of what a spectroscopist would see when looking at the spectral shape of these different objects. And so again, just another way of showing that these objects have very distinct spectral shapes that can be used to differentiate them from each other. So other objects might have much more similar spectral shapes or may appear to have the same color to our eyes, but absorb and reflect light in different regions of the electromagnetic spectrum in unique ways, and in unique ways that our eyes cannot perceive. Having the entire electromagnetic spectrum is a very powerful way to discriminate differences that our eyes are blind to. One way to get a grasp of hyperspectral imaging is to compare it to a more common or more well-known imaging technique. So a simple RGB imager that everybody has on their camera phone collects an RGB image as we are all accustomed to seeing. So if you break down what that sensor is actually doing, there is a blue filter that only collects light in the blue region of the spectrum, a green filter that only collects light from the green region of the spectrum, and a red filter that only collects light from the red region of the spectrum. And the pixels on the camera each have one of these filters over them. So you either are collecting a blue image, a green image, or a red image. And when you put the intensities of these images together and color one blue, one green, and one red, they form together to make an RGB image like we are accustomed to seeing. And another related technology is multispectral imaging, which instead of having 3 bands like an RGB image, can have somewhere in the range of 5 to 30 spectral bands with different ranges of spectral filters in those bands. And this can give you slightly more information by giving you the intensity in different spectral bands, but it still does not give you the spectral shape or the spectrum of each object. Where in a hyperspectral image, at each spatial pixel in your image, you will get a continuous spectrum over the entire spectral range of the instrument. This results in what we often refer to as the data cube, because it is 3-dimensional information with 2 spatial dimensions and the 3rd spectral dimension, which is illustrated here by showing that the data cube is essentially a bunch of 2-dimensional images or 2-dimensional grayscale images for each of the spectral bands in the imaging spectrometer. And if you look at any spatial pixel in this image, you can see the complete spectrum at that spatial pixel. And that will allow you to identify the chemical features at each of the spatial pixels in the image. So being able to identify the chemical features at each of the spatial pixels in the image is very powerful, because this spectral shape can be used to differentiate objects that might have similar spectral intensities in the bands that in your RGB bands or even in your multispectral bands. For example, in the set of spectra that I showed earlier, if your multispectral bands were at the points where the spectra overlap, they would all have the same intensity profile, and you would not be able to differentiate these very different objects. However, if you have a complete and continuous spectrum, you can use the spectral shape to identify these different objects, and you don't need to worry about whether or not the intensity at the bands that you happen to have give you enough information to chemically discriminate the objects. This illustration briefly talks about the extra information you get as you go from a simple monochromatic camera to an RGB camera to a multispectral camera with tens of bands, finally to a hyperspectral imager where you can get a complete and continuous spectrum and do anything with an image that a trained spectroscopist can do with a spectrum, including, of course, discriminating objects based on their chemical signatures, or even quantitative measurements based on the strength of spectral absorptions in the hyperspectral image. Finally, here is an overview of the different products in Headwall's hyperspectral imaging catalog. And they are categorized by the spectral range that they cover, and also the detector technology that is used in the focal plane array for each of those sensors. So our most common sensors are the visible near-infrared sensors that cover 400 to 1000 nanometers. And those all use silicon detectors, which are, of course, the most common and most well-developed detector technology. There are also extended V-near and near sensors that go out to 1700 nanometers using in-gas detectors. And finally, shortwave infrared sensors or SWIR sensors that cover 900 to 2500 nanometers that currently all use MCT detectors. So how do Headwall's hyperspectral imagers collect a continuous spectrum at every spatial pixel in a scene? So here we're going to go over how the hyperspectral imagers work. We're going to get a picture of the internal optics of the system and talk about how actually data is collected. To gather any digital image, a scene is divided up into pixels. So the most familiar way of thinking about something like this is to take a single two-dimensional snapshot where the full scene is divided into the amount of spatial pixels on your focal plane array. And then this scene is reprojected onto your camera. It saves it as a digital image where you have a different intensity value for each pixel in the scene. Headwall's imaging spectrometers are push broom imaging spectrometers that take an image of one sliver of the scene at a time. The image of the scene is actually projected onto a slit that cuts off all except for this one sliver of the scene for every time a frame is gathered on the focal plane array. And therefore, it requires movement of some kind to collect a whole scene in order to gather the other spatial dimension. So why do the push broom sensors only collect the image of a slit rather than the full 2D scene every time? Well, that's because we also want to gather spectral information. So we're not throwing away part of the focal plane, we're actually filling the whole focal plane, but one dimension is the spatial dimension, and the other dimension will be the spectral dimension. And so I like to think of this as having hundreds of spectrometers in a single box, where each of these lines along this dimension is like a different spectrum or a different spectrometer. So for instance, our nano hyperspec imaging spectrometer has 640 spatial pixels, which is like having 640 spectrometers in one box. So that means that when you gather this line and send it into the imaging spectrometer, it's dispersed in the other dimension, and you're getting all of the spectral information for this one spatial pixel projected onto the focal plane at once. And so in that way, for collecting this three-dimensional data cube, we are collecting one spatial dimension at a time and the spectral dimension. And then we need to scan in the other spatial dimension. And so how do the optics of the system work to achieve this? If we cut away and see how the optics look on the inside, this 4-optic lens is projecting the image of your scene onto a slit right here. And that slit is then put into a set of 2 concave mirrors and 1 convex mirror. And that set of optics will re-image this slit onto the focal plane. And so in simple terms, it's just taking the image projected onto this slit and then reprojecting it with no aberrations back onto the focal plane up here. However, we don't just have 3 mirrors. This convex mirror right here is actually a diffraction grating, which will disperse the light or make the blue light travel to one end of the focal plane and the red light travel to the other end of the focal plane, and spread out all of the frequencies of light to different locations on the focal plane. And in this way, we'll fill up the entire focal plane in one dimension with spatial information and in the other dimension with spectral information. So if we go back and look at this cartoon again, the figure on the left is what the scene would look like if we did not have a diffraction grating in our imaging spectrometer. And the figure on the right shows what the image on the focal plane looks like after the light is dispersed to move the blue light to a different spatial location than the red light and create a bunch of spectrometers again in a single package. Now, In order to collect the other spatial dimension, we need to have motion. And the way that that motion is depicted in this slide is by moving the sensor. So in the remote sensing world, it is easier to move the sensor than it is to move the sample or move the world under the sensor. So the drone will fly past the scene, and every time the drone moves one spatial pixel, a new frame is gathered. And in that way, every time you move one spatial pixel, you collect a new frame and collect a new frame. And after you've flown past your entire scene, you will have collected your entire two-dimensional image. And so if I animate that, here now I've moved the focal plane to be in the same orientation as I've shown here on the left. And as the drone moves one spatial pixel, I will gather another frame from the focal plane, which again, in this dimension is giving me spatial information, and in the other dimension is giving me spectral information. And as my drone flies past, and again, every time I move one spatial pixel, I will collect one frame on the focal plane and eventually build up an entire data cube. And that data cube is graphically shown down here, where again, we can see this is what the image looks like on the focal plane with the spectral axis in one dimension and the spatial axis in the other dimension. And then these are showing all of the different snaps of the focal plane as we are moving past the scene. So of course, if you're not flying a drone and rather taking images in a laboratory, you can move the sample and keep the light source and the sensor stationary. And so that's what's shown right here, where we have the imaging spectrometer above a sample stage and a light source that is projecting a line of light down onto the scene right where the sensor is looking. And then the stage can scan past the imaging spectrometer. And as the scene moves past the slit, just like in the drone, every time the sample stage moves one spatial pixel, a new frame is collected and we'll build up an entire data cube. In summary, this brief introduction to hyperspectral imaging shows that hyperspectral imaging is a combination of imaging and spectroscopy, and Headwall manufactures push broom imaging spectrometers that will gather one sliver of the scene at a time and push their way past the scene or sweep past the scene to collect the entire image of the scene. So Headwall imagers will collect a three-dimensional data cube, which will have two spatial dimensions and the one spectral dimension. The final result will be a data cube that is a two-dimensional image of the scene with a continuous spectrum at each spatial pixel. Objects in the scene can be identified based on their spectral signatures, and other information up to and including even quantitative information can be pulled from the spectral information in the hyperspectral image. Headwall's push broom imagers scan the other spatial dimension to collect the entire scene, and in that way, motion is necessary to collect the image of an entire scene. And the internal optics in Headwall's imaging spectrometers are an Offner relay, which is a very low aberration design that enables high quality, both spatial and spectral imaging. Thank you very much for your attention.